Hello and welcome to Build Your Own CPU Part 11. In this episode we'll be looking at the memory map and the memory access timings. The CPU has only got an 8-bit address register and everything in it is 8-bit, program counter and registers, so we can only actually access 256 bytes of memory, be it ROM or RAM. Because we've only got 256 bytes, you can't get much of a program in that. The CPU was designed to be just a demonstration of how CPUs work, but you want it to do something. So unfortunately, I had to go down the road of the paged memory map. So in that, you'd have a paged register and the CPU address. You join those two addresses together to give you your 16-bit address. And that'd be your memory address going actually out to your ROM and RAM chips. So the CPU can see page 0 or page 1 or page 2, all the way up to 256 pages. So CPU address is only the bottom 256 bytes though. So there we go, so you can put the 16-bit ROM in there, and you'd have a register, a physical latch, 8-bit latch for your ROM page. So you put your CPU address in it from your memory address register, so your address outputs from the CPU, and the ROM page 8-bit latch joined together to give you your actual address to go to the ROM chips, and that would access all the pages. Now, you can't get much for a program in just ROMs, so you need some RAM as well, because you need to push data around, and just having the R1 and R2 is not enough data space. So one way of doing this is to cut your memory into two chunks. So you would have your ROM sitting here at the bottom, and your RAM sitting on the top in your 256 bytes of addressable space. So you have your CPU address coming in, and a bit of a ROM page, rather than just a page register. We'd have a register, one for the ROM. We'll explain in a moment why. So you've got ROM 1 and a CPU, and join them together. You only did 7 bits of the CPU address, so you end up with a 15-bit ROM address. So that's 32 kilobytes of addressable ROM, but it's all in 128 byte chunks. So bit 7 of the CPU address is always 0. So if it's a 0, you're addressing the ROM, so you can use that in your chip select circuitry. Now your RAM, which is in the top half, again you only need the bottom 7 address lines from the CPU, and we'll have a separate register for the RAM page. So again that gives you a 15-bit address, but for your RAM, and they're all in, that's 32 kilobytes in all, but it's all in 128 byte chunks. And for selecting this, you could look at bit 7 of your CPU address is 1. So if it's a 1, it's RAM. If it's 0, it's a ROM. Now the idea of having two separate registers for your ROM and RAM page is that you could be running a program saying page 2, but it'd be able to access the RAM that's in, say, page 0 or page 1, wherever. So the two halves are separate. Also, what you could do with this is you could have like a monitor ROM sitting in all the ROM pages, and you could use that to load in another program in the RAM. So you can have basically your operating system sitting in ROM, or the ROM section, and then your application program you could put into the RAM section and run it from there. And when your RAM program's finished, you can switch back to the ROM, or you could configure the keyboard to let you escape back to the ROM, or whatever you wished. Now, the layout of this would be, here's your ROM IC, and you'd have your bottom 7 addresses going in here, along with your ROM page latch, feeding the top 8 bits, and then if A7 is 0, that'd be like your chip select for your ROM IC. So you have a 32K ROM. And for the RAM, you do the same sort of thing, set with A7 is 1 for your chip select. So again, can 8-bit latch at a different I/O location to the ROM one, and again addresses 0 to 6, and they just feed straight to your data bus straight back to your CPU. So that'd be quite a simple board to design and build. Just some ROM and RAM chips and a little bit of glue logic and a couple of latch ICs. So this is how the program actually changes the pages. The actual CPU itself doesn't understand the ROM or RAM paging. All it knows is it's got 256 bytes to run its program in. What we've got here, this is at the start of every page, this bit of code. In this case, we're looking at the ROM, so that's the beginning of every ROM page. And this is at the end of every piece of code that's in the ROM page. It doesn't have to be right at the end of the ROM itself, it's just at the end of your bit of user code. And you can have multiple ones of these throughout the program, so that you could jump to, you could have like a skip if 0, go to this page, if it's not 0, go to another page. So start with, we're going to use an out command, and we're going to take the value from that RAM location and put it into the ROM page register, which is at address 0. You could make that anything you wanted, but I've done it at 0. And this is just a RAM location, it could be anyone. We have to go via the RAM for a reason I'll show you in a moment. Now, what is in the RAM? When you first start up, that'd be a 0. 0 into there, so you're on page 0, and then the code will carry on executing from address 3, because that's 0, 1, 2, and then 3 for the next bit of code. Now, when you come near the end of your page, in this instance less than 128 bytes, you need this code in here to switch to a new page. So what you do is, say you want to go to page 2, we move the number 2 into this memory location, which is same as that one, into the RAM, and then branch back to the beginning. So this bit of code at the beginning is really the end bit of code, because what we do here is we take that value we just put in there and we put it out into the ROM page latch register. The memory will then immediately switch to the other page. The processor doesn't know this. All it knows is it's going to do address number 3 next. But the hardware has now switched us to page 2. So the code will come in at line 3, because the program counter here is still at the end of this instruction is sitting at 3. So it'd be 3 there. Once you run that bit of code, you'll go straight in here. Now, the reason we put this in RAM is because if we just said, I'll move 3 straight into the paged latch, it will change to the next page straight at this point, and we don't know where this bit of code is going to be in the program. It doesn't have to be right at the end. So we'd be jumping to an unknown location. So if we go through the RAM, we just put the RAM in, and then there, and we know we're always coming in at address 3. So every page the code starts at address 3. And again, when this page is finished doing its code, then we'll go to another page. You just put that number into RAM, branch to start, comes around to here, and it sets the page up, which page you want to go to, and the code for that page will be starting at 3 again. Now, if we want to do that in RAM, so if you had a 50-50 split, as described previously, the RAM starts at 80 hex. So we could do the same sort of thing using a different RAM page. We could use the same memory location, I suppose, because it gets overwritten. But I used a different one for this. So we're starting at 80 this time, because RAM starts at 80. Now, the usual code is the same as it is the ROM, and then the program starts at 83. So this would be like the application installed. And then when you run out of space there, before you hit this memory location, you do the move to the new page you want to go to, branch to the start, and that loads the new page in, which would jump you straight onto this one at this location here. So exactly the same as a ROM, but your addresses are a bit different. Now that that's all explained, hopefully you understand it, I didn't do that. I did this. Exactly the same, except instead of using half the memory for RAM, I only use 16 bytes. And all the rest at the bottom is ROM. The reasoning there is I didn't need that much RAM. And having only 128 bytes for your program, you're forever changing pages. With this way, I've got at least 240 bytes of ROM before I have to change page. So I had to use the whole address at the bottom here. So I ended up with a 16-bit ROM address to go to the ROM. But every 240 bytes, there's a 16-byte hole. But that's okay, you just have to keep skipping over it. And there's 60 kilobytes in total I can have for ROM. And the RAM, very similar again, but it's all in 16-byte chunks. So I only needed on the bottom here to put the 4 bottom address lines in, and the RAM page register joined onto that. It gives me a 12-bit address. So I could just use, that bunches all the RAM bits up together physically in the RAM chip. But they're all in 16-byte chunks. So I've got 4K in all for that. So this would be like the circuitry for that. If that was the ROM IC, that's the RAM IC. You put all the addresses in, and your ROM page for the top addresses. And if the address 4 to 7 of the CPU, if any one of them's got a 0 on it, then you must be in ROM. So chip select your ROM. Whereas on the RAM, if all A4, 5, 6 and 7 are 1s, you're in the top 16 bits. So you're in RAM, so chip select for the RAM. You only need the bottom 3 addresses onto the RAM chip, and your 8-bit latch will be on the next 8. So there's your 4K addressing. I say the RAM just goes on data bus, the same as the ROM, because the CPU doesn't know any different. Of course, I didn't even do that. I emulated it all on the motherboard. When I was building the motherboard with its PIC chip, and that was doing all the timing and the keyboard reading and the display, I thought, well, it's got ROM and RAM built in, why can't I use that to emulate it as well? So it's this same layout, I just emulated all this in the software. But if you want to do a chip, that's an easy way to do it with chips. So the ROM paging for this, same as before, except we can go a lot further before we run out of ROM. So the same as before, all comes in the same place. I did implement the RAM paging, but as it was, I didn't need 16 bytes of RAM, so I never actually bothered swapping pages for the RAM. So here we've got the actual timing for the memory. So if you want to connect up a ROM chip, or RAM chip, whichever you want, these are your read and write signals. Your address signals are normally there a long time before you're doing a read. They normally get set a clock cycle or two beforehand. So your address is set. Stress line's all there. And then you're coming up to whatever T state it is that's going to do the read. So T state will come on. This will generate then a memory chip select signal, which will come on. And you'll have your read signal on as well. You know you're reading and you're coming from a memory address. So that should all your signals should come on, and your chips then, or your memory chips should then go, oh, let's select the right data and put it onto the data bus. So this has to happen, well, the pulse signal here in this instance can be right back, could be back here. It won't make any difference because all the things happen on the down edge on it. But in reality, there'd be about a microsecond between this up and this up signal. So that, well, it depends what you've got programmed in your motherboard for your timing. So that comes on, all your data, it all stabilises, goes into your registers, and then when your pulse comes down, the data that was here is latched into the CPU registers. And then about a microsecond later, the T state will go off and your memory chip select and read will go off as well. So that's reading in. To do a write, it's similar but slightly different. Now your 6116 static RAM, or most static RAMs, allow you to do the clocking in on the chip select signal. Again, when you're doing a write out of the CPU, your address is normally all set up, well, it will be set up beforehand in your memory address register. Your T state will come on. This will almost definitely be T14. That will come on. then your data output will come on. Your data output is effectively your write, because your data output enable means connect the CPU bus, internal data bus, to the external data bus, but an output for a write basically. So that's basically your write signal. Data output write and read are two totally separate signals because they can both be off at the same time. That happens when you're doing an instruction load because the data doesn't actually go into the CPU. That's basically your write signal. Your write signal will come on and your T-state will come, or your T-state will cause the data output to come on. Memory chip select doesn't come on yet. So we're writing out, so the data outs come on with the T on, and the data comes out the CPU when the data output comes on, so it changes to the value that it needs to be. Then a short while later, the pulse will come on. And when that comes on, if you remember looking back on the T14 boards, you saw that it was handed in with the memory chip select. So that comes on as well. So now you've got your chip select for whatever chip you're going to. So your chip's on, select's on, your data's coming out, all your addresses will be there. So you set your memory chip up, and then that pulse will be a microsecond long. And as soon as the pulse goes off, your memory chip select will go off, and the data will be locked into your RAM chip. So you need a RAM chip that can work on the memory chip select falling to latch it in, which many of them do. So I hope that makes sense of the write timings. For the I/O, it's exactly the same. Using the read and data out, the only difference is instead of having memory chip select, you've got the I/O signal, an I/O signal there. So you know it's an I/O output or an I/O input, not a memory chip select. So again, they just come on together and get strobed into the CPU when the pulse drops. And then when you're writing out to the I/O, your pulse for your I/O signal is delayed till the actual pulse comes on, and then is latched out at that point there. Hope that makes sense. That's it for this video. A shorter one this time. A bit more to think about though. And hopefully I'll see you in part 12. And don't forget to like and subscribe and tell your friends about this channel.